Today I will tell you something about quantum state estimation. But first, why do we need it? Quantum technology would like to use information coded and transmitted by quantum channels, so adopting quantum states. That's why it's important issue to know the state sometimes and to be able to identify it. But in this sense, we must stress at the very beginning one important fact, namely that quantum state is not unobservable in the traditional sense of quantum mechanics. It means that it cannot be just measured. On the other hand, can be estimated. It means that some extra mathematical effort is needed, and all this is nowadays known as quantum tomography. So let's explain the basic facts. So in this sense, quantum mechanics tell us how the state, density given by the positive semi-defined density matrix, gives us some data. And once we have this data, quantum tomography should tell us how to reconstruct, how to find the state. To do this, we will need some elements of quantum measurement. So the basic fact is how to describe the measurement. The structure which is used for this is positive operator volute measure, but in our case would be absolutely sufficient. Is just von Neumann projections. These projections should create a probability. So the probabilities again should be normalized, and that's why the relation which is here is known as completeness relation. Once we have this, we should of course measure, so quantum mechanics predicts the probabilities. Probability in this case is given by Born rule as the projection of the density matrix into the set of measured states. And now the very last ingredients are data itself, because probabilities cannot be measured exactly, but they always be sampled in the form of frequency. So rho can be sampled by Ni divided n, when that Ni is number of the counts which appear on the channel, which corresponds to the projections, and these are the frequencies. Now we are ready to formulate some reconstruction protocols. The easiest way is to suggest linear inversion. To do this, it's enough to represent the density of matrix, density operator, in some generic operator basis. Let's call it gamma j. And then formulate the Born rule for these coefficients. In that case, you will take the projections into the von Neumann states. We will simply get Aj times gamma ji equal to I, where, of course, gamma ji equal to projection gamma j and of course this is a sort of linear equations, and at least formally we will write it in vectorized form. I can write A equal to gamma minus 1 times F. Of course, the tricky part, what does it mean gamma minus 1? Because now it depends on the dimensionality of your space of detected points or your parameter space. But this, we don't need to go into the detail. The issue is that in all this procedure, there is no guarantee that the condition of positive semi-definiteness is fulfilled, so you can't believe that we will get it. Good. Now we are ready to formulate the second alternative, and let's talk about maximum likelihood estimation. In this way, what we will formulate first is the likelihood. And you should understand likelihood as the kind of probability that your particular data, which are represented by frequencies, appear. So, likelihood, as it is usually defined, of course, is for the data, is conditioned by your state, and is nothing else as product of all probabilities with their frequencies which appear in the channel. So it is something like that. Of course, it's much more convenient to work with the log likelihood, and it gives you essentially the same result. So log likelihood will be, in this case, the sum, weighted sum of the logarithm of probabilities with the weights which correspond to the frequencies. And of course, we are aware of the fact that density matrix is normalized to 1 as the trace. And now the philosophy behind the maximum likelihood is quite simple. We know that the data could appear in principle for any state, but not equally likely. And this estimation procedure, this reconstruction, is simply asking, once we have the data, what state will make our data most likely. And in this sense, we can formulate the extremal equation, which simply corresponds to the maximization of likelihood under the given constraint. I will just write just formally. And it is log likelihood minus lambda branch multiplier of density matrix equal to 0. I will not go to the detail, but it's quite a simple exercise because the variation looks like formally like derivative with respect to the density matrices. And what you get in here is extremal equation which you should solve. And the extremal equation looks like that. You have frequencies, your data, divided by probability, which depends on the state, times projectors. And this should equal to 1 on the subspace where density matrix is defined. What helps us a lot is to see this as a new POVM element, namely with the prime. You see the difference is just in the normalization. And that it is. It's all. You probably don't see the analogies between linear inversion and maximum, but they are. And I will emphasize, what we are doing here is that we are taking the equation for the Born rule and postulate that they should equal to frequencies, and we are solving this as the equation, solving in linear way. On the other hand, what is guaranteed is that POVM element, which correspond to this, which would, if you make a trace, gives you the probabilities, are of course equal to 1. So this is identity. It means that you cannot get any new piece of information from that. But now look on the structure of maximum likelihood estimator. As I said, here we have some Euler-scale POVM elements. So let's see them as the element which generates new probability, which is simply given but as a trace of pi prime rho. Now you see what happened. You will make, I will write it explicitly, Fi divided P, rho times Y, projections into the von Neumann state. But these two things are the same. So this equals to frequency as an identity. You cannot derive any kind of information from that. But on the other hand, just give a look on the extremal equation. It's nothing else as complete this relation for this new rescaled positive operator volume measures. And now, in the next part, we will show why it's so. What is the natural physical explanation behind this structure? And how to understand to this result? Actually, the leading principle is quite simple. It tells us that more noisy detection is simply less credible. Let me show you an example. Think about the polarization. So imagine that you have a true state oriented in this way. The state of polarization, and what are you doing? You are now orienting your polarizer according to various directions. If it happens that your polarizer is oriented along the true direction, the detection is naturally deterministic. You can even think about coin tossing experiment. In this case, of course, you will get only the results which are oriented along the true direction, just like if you are tossing the coins which have, for example, two tails, you are getting always the same result. So if you see this, the experiment, it's 1, 1, 1, whatever you are measuring is 1. It means in this sense, when you will start to calculate the mean value for these averages, it's the same, it's exact. On the other hand, you may have another polarization. For example, the orthogonal one. It would correspond to the well-behaving coin which have tails and heads. If you are tossing the coin, so this is configuration 2, what we get is just random sequence of the numbers. 1, 0, 0, 1, 1, 0, whatever. In principle, 50 to 50 in the regular coin, but depends on the orientation. So this is example where this is less noisy. Actually, there was no noise at all there, and it is more noisy. And what is the moral now? We should register many such orientations, and we should use them in our reconstruction algorithm. But on the other hand, all these projections are not equally credible from the point of view of this added noise. And in this real experiment, you don't know what is the part which corresponds to the signal, which corresponds to the noise. It's just number of the counts what you have. And on the other hand, you cannot even see it because you don't know what the true state is. And this is the reason for this nonlinear algorithm. And what maximum likelihood is doing, it in certain sense estimates the state, the true state, and gives the credibility to your data. At the end, simply infer the state which is the most likely. And another issue was the positive semi-definiteness. It's really very important because, as you know, everything related to uncertainty principles, incompatible variables, etc., depends strongly on this positive semi-definiteness of density metrics. And in our equation, which was actually formulated as the equation for the operator R, Fi, P, I rho equal to 1. So it is a kind of definition. It was not clear how could you guarantee positive semi-definiteness. It can be done if you do several easy steps. For example, take this equation, where r equal to 1, and multiply from the left and from the right by density matrices. So what you will get is rho r equal to rho or equally r rho equal to rho. And of course, you can take, for example, this equation, multiply again by r from the left, and apply again the same rule, and what you will get is r rho r equal to r rho equal to rho. So there are many equations like that, and the main thing about here is that you will use this for iterations. You will start from some positive semi-definite solution. You will be always operating in the in density matrices. Or you can, of course, use some more sophisticated convex optimization to get a solution of this nonlinear matrix equations. So this will gives you well-behaved solution, which at the end guarantees the condition of positive semi-definiteness. But last remark is necessary to make. Don't forget, even the most likely state is not the true state. That's why if you would like to use this maximum likelihood state estimation, some more subtle error analysis of error bars is needed.